So let's go to what is time domain analysis and what is frequency domain analysis. So when I represent a signal in time domain, all it means is I'm just plotting the signal over time. So time domain representation, if you just see this here, displays change in signal over a span of time. Which I'm just plotting the signal, how the signal varies over time. So it could have a peak value, it could have a minimum value, it could be periodic signal, it could be aperiodic. There are many characteristics that I can have of the signal over when I plot it over time. But when I analyze the signal, when I display the signal over time, how it varies over time, that's called time domain analysis. And the right side represents the frequency domain representation of the signal. This shows what are the frequency component of that signal. So typically, and I will explain that a little bit more, but typically the time domain is represented with the small letters. So in this case, my signal is x of t, which is varying over time. So x of t, and in frequency domain, I represent it as capital X of f. X of f is a function of f. So in this example, x of t is varying over time. In frequency domain, it has frequency components from minus fx to plus fx, which is the frequency values. And the y-axis here, if you see that it is mod of x of f, so the y-axis represents the amplitude of each frequency component. So another way to say it is, if I could generate sinusoidal signal from minus fx to plus fx, and I generate signals with the amplitude representation represented by this graph, and if I add all of them up, I'll get back the original x of t time domain signal. To understand that a little better, let me give an example of human speech. We all know our audible speech ranges from 20 hertz to 20 kilohertz, which means I any sound that I can hear or I've ever heard in my lifetime, whether it's my speech or it's band, it's a Beatles music or it's some instrument. If I could generate sinusoidal audio frequencies from 20 hertz to 20 kilohertz, I could combine them in various combinations and I could generate every possible sound that I can hear. So in other words to say is every sound will have frequency component somewhere between 20 hertz and 20 kilohertz. Again, it need not have the entire range of frequency component, but it will have some component between these two. So instead of any speech I can represent using its frequency component. So that's what this is doing. In time domain, this is how the signal is varying with time. In frequency domain, it's showing what frequency component that signal has and what's the amplitude of each frequency component. That's what the frequency domain represents. Now, now going further, let me just clear these things. Now, how do I if I know the time domain signal, how do I get the frequency domain signal? So the mathematician Fourier has a well-defined formula. Again, we'll not go into the details or the proof of that, but we can cover that if needed. The procedure of converting from a time domain to frequency domain is called Fourier transform, and a procedure to convert from frequency domain back to time domain is called Fourier inverse. The formula of Fourier transform is capital X of f. As I said, the frequency domain is always represented with the caps letter. Capital X of f is integral minus infinity to infinity x of t e power minus j 2 pi f t dt. And the formula for Fourier inverse is x of t is minus infinity to infinity capital X of f e power plus j 2 pi f t df. So this is Fourier transform, and this is Fourier inverse formula. Now if you see here, so a few things to notice here is, in frequency domain, in the Fourier transform, you have something called j, which means it's a complex number. You're not going to always get a real signal in frequency domain. You are going to get a complex number. So what does this complex number mean? Obviously there's no complex real world signal. So what does it mean? So to understand that a little bit better, we'll go into detail about a complex number, but one thing I want to to show is, here we talked about the each frequency component and the amplitude of frequency component, but each frequency component not only may have different amplitude, it may also have different phase delay. So every frequency you may have to apply different phase delay in each frequency component to get back the original signal. So that's why the complex number comes into picture. And let's go into a little more detail in the next page. So before I go into what frequency domain represents, some quick recap of basics of complex numbers. So any complex number we know has a real part and an imaginary part. So in a standard, if z is a complex number, in standard form, it's represented as a plus jb, where a is the real part of the complex number and b is the imaginary part of the complex number. So that's the standard form of complex number. But I can also represent complex number in polar form. So how to convert from standard form to polar form? So if z is equal to a plus jb, if I multiply it by root of a square plus b square, which is the magnitude of complex number, so I can write it as a root of a square plus b square into a by root a square plus b square plus j into b by root a square plus b square. And if I take theta as tan inverse b by a, which is nothing but the argument of complex number, which is tan inverse of imaginary part by real part, then I can represent this z as root a square plus b square into cos theta. So a by root a square plus b square is cos theta, b by root a square plus b square will become sin theta. So I can represent it um, as root a square plus b square cos theta plus j sin theta, or mod of z e power j sin. So we all know this is Euler's theorem. Cos theta plus j sin theta is e power j theta. So a complex number in polar form can be represented as its magnitude into e power j theta, where theta is the argument of that complex number. So in now coming back to our original discussion on the frequency domain representation, if my frequency domain representation x of f, if x of t is the time domain signal, x of f is the frequency domain representation. If x of f is complex and I represent it in polar form, the magnitude of the x of each x of f represents the amplitude of each frequency component, and the argument um, of x of f represents the phase delay of each frequency component. So that's the physical significance of the magnitude and the argument of the complex number. So let's say, as an example, say this is my x of t. This is the time domain signal, so I'm just plotting it how x of t varies over time, and say its frequency component is from minus fx to plus fx. This is mod fx of, this is the magnitude of x of f. So it's like a triangle in this example, and say the argument is from minus fx from 0 to plus pi by 2 and back to 0. So for each frequency component, the top graph shows the amplitude and the bottom graph shows the how much phase delay I should apply. So in other words, if I could generate sinusoidal frequencies ranging from minus fx to plus fx, and if I generate them with amplitude represented by this top graph, and then I apply a phase delay represented by this bottom graph, and I add all those frequency components up, I'll get back this time domain signal. So just to repeat that, if I could generate sinusoidal frequencies from minus fx to plus fx, so that minus I generate a sinusoidal frequency minus fx, its amplitude is 0. So then I take another frequency, say f1, I apply an amplitude which is represented by this, and then I apply a phase which is say 3 pi by 4 or something, and then I repeat the same procedure for all the frequencies from minus fx to plus fx, and I add all of them up. I'll get back this original um, time domain signal. So that's the meaning of frequency domain representation. And why do we have complex number? Because if I didn't have a complex number, I would not be able to represent the phase delay. I could still have a single value which could represent magnitude, but in order to show phase delay, you need two components. So typically you need, so the argument of the complex number is the, and we'll go into a little more why the argument is phase delay. We'll go into a little more detail as we go further in this class. But at high level, to understand is the magnitude of complex number of x of f is amplitude of frequency component, argument is the phase delay of each frequency component. Now before we go further, let me just go to the basics of how a sinusoidal signal looks. So we know, let's say y of t is a sinusoidal signal of frequency fc and amplitude a. So I can represent it as y of t is equal to a cos 2 pi of ct. This is just a simple cosine signal whose magnitude is a, amplitude is a, and the frequency is fc. Now if I want to apply a phase delay of theta, which could be pi by 4 through any angle, then the representation will be y of t is a cos 2 pi of ct plus theta. Now we all know from trigonometry, this is cos a plus b is cos a cos b minus sin a sin b. So if I expand this, I can get a cos 2 pi of ct into cos theta minus a sin theta into sin 2 pi of ct. So you can see here cos 2 pi of ct is a sinusoidal signal. Sin 2 pi of ct is also a sinusoidal signal with 90-degree phase shift. Sine is nothing but a cosine with a 90-degree phase shift. So this is my sinusoidal signal with frequency fc with zero phase shift. This part is sinusoidal signal with same frequency fc with a 90-degree phase shift. So the amplitude of my sinusoidal signal with zero phase shift is called the in phase component, and the amplitude of the sine signal, which is a 90-degree phase shifted sinusoidal signal, is called the quadrature phase component. So a cos theta is my in phase component, a sin theta is my quadrature phase component. So any signal with a phase shift can be generated using an in phase component and a quadrature phase component. If my theta is 0, if I don't have any phase delay, it will have only in phase component. If my theta is pi by 2 or a multiple of pi by 2, um, pi by 2, 3 pi by 2, 5 pi by 2, then it will have only quadrature phase component. But for any other phase delay, I the signal will have a in phase component and a quadrature phase component. Often as you go into further discussion, often signals are present in terms of in phase and quadrature phase component. So so coming back to our Fourier transform, when x of f is complex, the real part of x of f is my in phase component of that signal, of that frequency component. The imaginary part is the quadrature phase of component. So in this example, my a cos theta is my real part of x of f, a sin theta is the quadrature part. So obviously if I divide this, I get tan theta, which is my overall phase shift. So that's why the argument is the overall phase delay of that frequency component when I combine both in phase and quadrature phase component, and mod x of f is the overall amplitude of that frequency component combining both in phase and quadrature phase component. So this is just some another way of looking at the x of f. What is the real part, which is the in phase component? What is imaginary part? That's the quadrature phase component. If I just do square root of real part square plus imaginary part square, which is the magnitude of x of f, that's the overall magnitude of frequency component combining in phase and quadrature phase component. Argument is the phase delay of the overall frequency component, again combining both in phase and quadrature phase component. Now some of the intuitive things based on what we learned. So if we go to and to Fourier, let's say x of t is even. Even means x of minus t is same as x of t. For example, cos signal is an even signal. So when x of t is even, we know cos is an even. So that means I should be able to generate with only cos frequency components, which means it will have only in phase component and it will not have quadrature phase component for a pure even signal. So x of f will be real only, since in phase component is the real part of x of f. So x of t, when x of t is even, x of f will be even, it will be real only. There is a mathematical proof for this, but this is just an intuitive way to look at it. Why x of f would be real only when x of t is even. Similarly, if x of t is odd, then you can generate using a sine signals, which means it will have only quadrature phase component, and we know in x of f the imaginary part is a quadrature phase component. So when x of t is odd, x of f will be imaginary only. Again, there's mathematical proof for this, but this is some intuitive way of why this is the way of looking at it. What is the physical significance of this Fourier transform property? But many of the signals are neither even nor odd. In that case, your x of f will have both real as well as imaginary part. So hopefully this helped you understand very high level basics of digital communication and what is a frequency domain and what is a time domain representation. What is the meaning of the real part and the imaginary part of frequency domain representation. um, so in the next class we'll go into details of what we call as Nyquist theorem and the proof of that. So thank you very much.